All right, so now we're getting into the interesting math here. The dot product tells you how aligned two vectors are. It's incredibly important. It's used in lighting calculations. It's used a lot of times when I want to determine if an object is facing another object or away from it. If you were making a stealth game and you needed to find out whether or not you're behind the character, you could use the dot product to see if you're behind or in front of that player. It has a lot of really good uses, okay? So what we need to understand is that the dot product is one of two methods of multiplying vectors, and the dot product is going to give us a single scalar value. It's going to be a value between -1 and +1 if we're using unit vectors. So the dot product is nothing more than the cosine of the angle between the two vectors, cosine of b. Now, usually you never know the angle because you're dealing with vectors, not angles, okay? But the good news is that you can use the values of the vector to calculate the dot product, and that's what we have down here. So we have AD plus BE plus CF, all right? So the idea behind that, and unfortunately I didn't put it up here, well, you know what, I'm gonna composite something up here right now through the magic of video editing. But the idea is that you multiply like components. It's the x component in one vector times the x component in the other one, plus the y component times the y component, plus the z component times the z component. That's why you get a single value out of this, because you're basically multiplying like terms and adding them all together for your final answer. As I mentioned, the dot product is incredibly useful in our shaders for calculating the diffuse lighting calculations on surfaces. When two vectors are parallel, the dot product, when they're unit vectors, will return a value of 1. When they're 90 degrees apart, it will return a value of 0. If they're anti-parallel, you get -1. Let's do an example of the dot product on paper to make sure we understand the concept of what's going on. Now, I mentioned before the dot product is going to produce a single scalar value. So long as we're dealing with unit vectors, the output is going to be very simple to understand. So let's create a few vectors. Let's make one called V1, and let's do another vector. We'll do this one anti-parallel, V2, and then let's do another vector that's going to be 90 degrees. Okay, so that's V3, right? So let's go ahead and start taking the dot product of V1 with itself to begin with. So let's create some numbers to work with. This looks pretty easy. Let's just do 0, 1, 0. Remember, this is the x, y, and z. For this one, it's going to be 0, -1, 0. And for this vector over here, we're going to give it the values of, let's see, we'll do 1, 0, 0. And remember, this of course all pertains to x, y, and z values across here. So if we were to dot V1 with itself, what we would end up with is the following. So V1 dotted with V2 is going to be equal to, let's write this out long ways. So we're going to take the x terms, 0, the y term 1, and of course the other term z, 0, and once again we'll write that a second time, 0, 1, 0. Remember, we multiply these together, so it's going to be this times this. If you want to look at it that way. Then if we of course add each of these to each other, what we're going to end up with is 0 times 0, which is 0, plus 1 times 1, which is 1, plus 0 times 0, which is 0. So we get a value of 1. And this is going to be true anytime we deal with two vectors that are parallel, and of course if they are both unit vector. If they're not a unit vector, you're going to end up with some value that is not 1. It could be greater than or smaller than 1 depending upon what you're working with. What about anti-parallel? What happens in that case? So let's do V1. We're going to dot it with V2. Alright, so what do we end up with in this case? Well, let's put our x, y, and z terms down as before. In the case of V1, it's 0, 1, 0. In the case of V2, it's 0, -1, and 0, right? Once again, we're going to multiply these together and sum them all together afterwards. That produces a 0, produces a -1, and that produces a 0. Therefore, when we add all together, we get a value of -1. All right? So, when you're anti-parallel, you get a value of -1. All right, so what about in the case of this right angle? So if you think about it, V1 is going to be perpendicular to V3. Hopefully you see where I'm going with on this one. Hopefully maybe you can even already kind of figure out what the value is based upon parallel being 1 and anti-parallel being -1. So let's do V1 dotted with V3. All right. We're going to take the x, the y, and the z terms as before. Just set that equal over there. So the green terms, 0, 1, 0 for vector 1. For vector 3, it's going to be 1, 0, 0. Multiply, 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 and add. Well, this becomes 0, this becomes 0, and this becomes 0. So we end up with a value of 0. So when you're perpendicular, your value is 0. Let's look at an example of how we can use the dot product successfully inside of Unity. So I brought in 2 assets already to this new project. The first one is an eyeball. There it is. We'll reset its location. So this is going to be looking around, and there are going to be several creepy dolls that are trying to get to it. Here's one of them right there. Reset that guy's position as well. Now the idea being that the dolls will slowly be moving towards the eye. However, if the eye is looking towards them within some angle, will determine the doll will freeze and stop moving. But then as soon as the eye continues to look beyond that doll, it will move towards it. So we're going to need a couple scripts. One script will simply spin this eye around endlessly around the y-axis. The other script is going to be attached to several of these dolls. Let's just duplicate this guy a couple times. And there we go, Control D to duplicate. And now all we need to do is create the scripts. So let's right click, create C# script. Let's call this, iSpin, not iSpawn. Let's rename this inside of MonoDevelop. Double click. Yes. So here we are. Let's rename this. Right click, refactor, rename to iSpin. This way the name is also changed for the file. Unity will also change its name once we come back in. We don't have to worry about there being a conflict between the class name and the actual file name. Now inside of start, we don't need to do anything. All we need to do is constantly spin this object. We need the transform for that. So let's do GameObject.transform. Let's see. Let's just do rotate. So we can just pass in an Euler angle in this particular case. Or we can do several different ones. We can specify a vector 3 axis. Well, I do know my vector 3 axis is going to be straight up, so let's try that one. So let's do a vector 3.up. And what should our angle be? How about just, I wonder, well, let's create an angle speed first. So let's do float, public float. Rotation speed is equal to, let's just set this to be 1 degree per second. We'll grab that rotation speed, place that in there. Since this is a speed, in order to use this term properly, we need to multiply this by time.delta time. Now this should continually rotate our object around the up axis, an amount of time that has passed times the rotational speed. Let's go ahead and put it on our object, our eyeball. There he is. Grab our script, throw it on there, and let's go ahead and hit run and see what happens. There we are. It's very, very slowly moving. Let's see if we can increase that speed a bit. That's 7, that's 9, that's 14. Let's give this eye a little bit better speed there. Maybe 40? Yeah, we'll go with 40. So let's stop. update that rotational speed, save the scene, and now we can go ahead and create our dolls. So let's create a new script, create, folder, C# script. Let's call this dolls, or just doll. Double click on it to open it up in MonoDevelop or Visual Studio. We're actually going to use something similar to the script we did during the subtraction. We're going to want to move our doll towards the eyeball object. You'll notice, however, the rotation's all off as well. They're looking all over the place. We're going to need the transform to move towards. So let's do a public transform. Let's call that target. Let's also do a public float and call this max speed. Well, actually, not max speed, just speed. Max speed would be for something different. So a couple ways we could do this is we're applying the transform here. I'm kind of lazy. I actually don't feel like manually placing this transform on all these objects, although I could just select them all, do a search, and then do it. Yeah, we'll do it this way. Or we could do it in Start and try to find that object. Anyway, so what we want our dolls to do is move towards that target. This is going to be the same procedure as in the past video. Let's just do a vector3 difference is going to be equal to the target dot position minus GameObject.transform.position. Let's do a difference dot normalized to normalize that vector. And now let us determine how far to move it. So let's do GameObject.transform.position plus equals difference times our speed times time.delta time. So in order to make sure that our dolls look in the right direction, what we're going to want to do is use the look at command. This is kind of a cheat. There are better ways of doing this, but this one will work just fine. Let's see. Vector3 look at is going to be equal to GameObject.transform.position plus difference. So we want to look from where we are to where we need to go, and that's what that line is going to provide us with, a vector in the direction we want to look at in world space. Next up, we're going to use GameObject.transform.lookAt. And in lookAt, we're going to use transformTarget.vector3worldUp. So let's do lookAt is the place we want to look at, and our world vector is going to be which way's up for us. And I want to always keep up in the global sense. So let's do a vector3.up. Let's go ahead and run this now. Okay, there's our scene. Let's, as you can see, our guys are constantly moving towards this one eyeball. If I move this up, you'll see now they're rotating towards that eyeball and down and so forth and so on. Whee! So now we're going to want to limit our movement. What I mean by that is we're going to want to stop moving if the eye is looking directly at us, or within a cone, or within some sort of a range. Let's actually add a new public value, public float range. The idea behind this is how much leeway are we going to give these guys before they notice that they're being watched. So we don't want to do any of this. We don't want to move. We don't want to do a thing unless we're within a certain range. The vectors we're comparing, and I'll put something up on the screen right now. The vectors we're going to compare here are the forward vector of the eye. Because it's constantly rotating, its forward vector is constantly moving. So let's store that really quick. So let's say vector3 eye forward vector is going to be equal to the target dot forward. The next thing we want to do is compare where we are in reference to the eye. We've actually already done this with the difference vector. The distance vector is how to move from that target to the eye. But if you invert that vector, if you multiply it by -1, it'll take us in the opposite direction from the eyeball to the to this particular doll. So let's just do vector3 inverted difference is going to be equal to difference times -1.0f. So now all we need to do is do an if check. And we're going to do, oh, well, truthfully, we also need to normalize these vectors. So let's do I forward vec dot normalized. And also, let's do inverted difference dot normalize. Make sure they're They're perfect. Now we just need to dot product these two. So let's do vector3 dot dot. And let's do I forward vector and now inverted difference vector. So if this dot product is going to be greater than our range, which means it's positive and that it's looking towards it, then we're going to commit all of this code down here. Else, we do nothing. So let's go ahead and hit run. Go to our game view and see what happens. And as we can see, the eye is rotating around. Oh, I'm sorry. I did the exact opposite of what I wanted to do. In this case, the eye is looking. When it looks at these dolls, they'll actually start moving towards it. So let's move this away. Stop it. So what I actually want is for this to be less than the range. So now, if it is less than 0.5, which means it's for all the way from values of -1 up to 0.5, they'll be allowed to move. But as soon as the vector returns a product greater than, a dot product greater than 0.5, the doll will stop in its tracks. Save that. Come back over here and hit run. And of course, let it rotate around. And here we can see once the doll sees the eye seeing it, the dolls will actually stop. Uh-oh. Here they come. Better run. Better run. Oh, no. Okay, and here we go. Stop. So all I have to do now is make sure the eye constantly travels in an arc around the dolls, and the dolls will never get a chance to actually come after me. Interesting. Well, anyway, that's looking at the dot product. If you enjoyed this video and you want more, please like and subscribe. Or if you didn't like something, make sure you write it down in the comments and let me know so I can make changes. Thank you. Bye.